So in this video, we're going to be introducing a new type of circuit called an operational amplifier, or op-amp for short. So what we're going to see throughout the next few videos is that these operational amplifiers are actually capable of performing a lot of different mathematical operations, hence the name operational amplifier. We're also going to see that these operational amplifiers are typically going to be used in analog circuitry, but of course we can use them with our digital circuitry as well. So before we get into sort of what our circuit symbol is and what our inputs, outputs, all of that stuff are, I just want to note quickly that our operational amplifiers are actually going to be packaged in something called an integrated circuit. And so we'll see in the lab what these look like. So we can call these ICs. But basically if we have sort of an aerial view, it's going to be this small piece of plastic looking stuff. We'll have a circle or a notch on one end to help us get our sort of our orientation there. And then for most op amps, we're going to have 8 pins. So these are going to be 8 little metal pins coming down from the side of that where we can put it into a circuit. So again, this is sort of a top-down view. And this is roughly the size of your fingernail. So what is inside of this plastic packaging, though, is we're going to have a couple components we're familiar with. Of course, we're going to have resistors, we're going to have capacitors, but we're also going to have a component we haven't talked about yet, and we actually won't talk about this component much in this class, but we'll get more into that in our next class, analog devices, which is transistors. So the actual circuit of our op amp looks like something here on this next page. So everywhere that we have these Qs, so let me switch to a different color. So everywhere we have these Qs, these are all our transistors. We can see, of course, we still have several resistors throughout here, as well as capacitors. So this seemingly really complicated circuit is going to give us our op amp, but for now, we're not going to worry about what's going on, under the hood, so to speak. We're just going to worry about how do we control our op amp using these 8 pins available. And as we're going to see in our lab, all 8 of these pins aren't even used. So we're sort of taking a high-level look here, and then in some later classes we'll get into some more details of various parts of this circuit here. Okay, so sort of taking a step back then, let's just look at our basic circuit symbol for our op amp. So our circuit symbol. So we're going to have a triangle shape, and we're going to have a negative and a positive. So coming into our negative, we're going to have one of our inputs, let's call that V1. Coming into our positive terminal, we'll have another input we can call V2. Then we'll have an output coming out over here on the right, how I've drawn it. And then we also have 2 terminals here, which are biasing the device. And so let me just write beside these what each of these are. So our V1, because this is connected to our negative terminal, we're going to call our V1 our inverting input. And our V2, because it's connected to our positive terminal, we're going to call this our non-inverting input. And we'll see a little bit later on in some later videos why these are called non-inverting and inverting inputs. And of course, as I said earlier, this V out is of course going to be our output. And then we have our 2 V plus and our V minus, which are our 2 power supplies. So this up here is just going to be our positive power supply. And down here, of course, we have our negative power supply. Oftentimes, we'll have symmetrical power supplies. That is to say, if our V plus is positive 5, our V minus will be negative 5, but that doesn't necessarily have to be true. So obviously this diagram can be a little complicated when we have all of these sort of terminals coming off of our triangle. So oftentimes what we'll use instead is we'll keep this negative positive. We have our V1 and our V2 and our V out, but we won't necessarily explicitly draw our biases. So typically we're just going to use this, and that's just to kind of reduce clutter of our circuit without having that plus and minus. One thing to note, and we'll see this in the lab, is that our output voltage, V out, cannot exceed those bias voltages. So V out cannot exceed V plus in our positive direction, and it cannot exceed V minus in our negative direction. And so really it's not going to be exactly V plus and V minus, it's going to be approximately V plus and approximately V minus. And so basically what what's happening here is something called saturation. So basically we can't have our output exceed the value of the voltage that's powering our op amp. So maybe we're powering it, let's say for instance we're powering this with a plus 5 volts and a minus 5 volts. If we put some inputs into here such that our output wants to be 8 volts, it's not going to be able to reach that, but instead it's going to be limited by this positive 5 here. So just something to keep in mind. We're not going to talk about that too much in this introductory course, but we will see that effect in our lab. Okay, so we have two ways that we can look at this op amp. We can talk about an ideal op amp model and a non-ideal op amp model. So first we're going to introduce the ideal op amp model. That's what we're going to be dealing with in this class, but I do want to at least write down and show you all the non-ideal model just so you're aware of what it looks like and how it differs. So what we're going to do is draw an equivalent circuit for our ideal op amp. So this is for our ideal case. So I'm just going to draw a triangle again. I'm going to draw it a little bit larger because I'm going to put some things inside. We're not going to get quite as complicated as that really sort of in-depth circuit we had earlier with all those transistors, of course. Okay, so we still have our V1 at our inverting terminal, our V2 at our non-inverting terminal, plus and minus like that. And we're going to have our output coming over here. But we're going to have our output in here connected to a dependent source. So a dependent source, again, we represent with a triangle, and we're going to have that reference to some common point. We have that labeled as ground. Okay, so let's say we have some voltage difference between our two inputs of VD. So let me switch to blue. So let's say we have some voltage here, positive on our non-inverting terminal, negative on our inverting terminal, and let's call that voltage VD. So what that VD is going to be, we're going to call VD our differential input voltage. And so like we can see from doing a KVL around that sort of pseudo loop there, or just from looking at the voltage difference between the two, we can say VD equals V2 minus V1. Okay, so what we're going to say then is this value of our voltage source, which I forgot to label here, but this is our V out. So this dependent voltage source is essentially setting what our V out is, and we're going to say that that value is equal to A naught times that differential input voltage VD, where A naught is going to be defined as our open loop voltage gain. So what we're going to see in some later videos is that the basic operation here is that we're amplifying the difference between these two inputs. And so we're amplifies difference between two inputs. And so it's being amplified by this A naught, which is some inherent property of our amplifier, and it's creating a single output signal. So of course here's where we get that name amplifier. These are operational amplifiers, and like we're going to see later on, we can use these in circuits to sum, to integrate, to differentiate, take the difference. We can do all these different mathematical operations, and so that's where we get the name operational amplifier. We're not going to look at it explicitly, but there are, of course, many different types of op-amp circuits, and in some cases you might use one over another because it has better characteristics for your operating region. For instance, maybe you're operating in a higher frequency Maybe you want larger gains. There are different amplifier properties that you might want. So now let's just briefly look at the equivalent circuit for our non-ideal op-amp, and we'll kind of talk about a little bit how this varies a little later on, but for now I just want to at least bring it up. So now we still have our inputs V1 and V2, but instead of having an open circuit between them like we have in our ideal case, we're going to connect these with some input resistance that we're going to call Ri. And so we still define our differential input voltage VD between V1 and V2 like such. And we're still going to have this dependent voltage source connected here, but now we're going to have an output resistance, R0, that's connected between the voltage source and the output. So we have some dependent voltage source here, reference to ground, and this is still going to be A0 times VD. So essentially the only difference here is in our non-ideal op-amp, we've added this R0 resistor and this Ri resistor. And like we'll see in the next video, typically this value of Ri is very large and R0 is very small, such that this ideal approximation is pretty good. So that's all for our introduction to op-amps. In the later videos, we'll get into some actual circuits.